In the last session, I showed the relation between the kinetic energies and the work. In this session, we'd like to introduce the potential energies. Energy seems to associated with the body's weight and height. When the ball is in the high positions, the ball has the gravitational energies. When it is dropped, it loses the gravitational energy and gain the kinetic energies. I'd like to show how to calculate such a gravitational energies and the relation with the kinetic energies. When you try to move the ball from the lower position to the higher positions, we need to apply the force to change the positions. We consider the body moves vertically from the initial height of the y sub 1 to the final height of the y sub 2 by applying the force. Work done on the bodies by the external force against the gravitational force is conserved as a potential energy. So in this case, the gravitational force of the mg is acting on the ball object. Then we need to apply the external force of the mg is upward, is against the gravitational force to change the position of the object. So mg is applying to move from the initial y sub 1 to the y sub 2. We'd like to calculate how much work is done by the external force. Is a W sub external is equal to the mg y sub 2 minus y sub 1. This is the work done by the external force. Work done by the external force is stored as a potential energy. So in this case, by comparing these two equations, we could introduce the gravitational potential energy. U sub graph is mgy. Then we'd like to show you the conservation of mechanical energies. So work energy theorems show us the relation between the kinetic energy and the work. So W equal K sub 2 minus K sub 1. So in the last slide, I show you the relation between the external work with the potential energy. So I showed these relations. External work is equal to U sub 2 minus U sub 1. But the external work is exactly equal to minus W. So direction of the force by the gravity is directly downward. Applied external force is opposite direction with respect to the gravities. So it becomes, you should put the negative sign. So W sub external equal to minus W. So this means this is equal to the U sub 1 minus U sub 2. Moving the K sub 1 to the right, U sub 2 to here, then we have this relation. K sub 1 plus U sub 1 equal K sub 2 plus U sub 2. K plus kinetic energy and potential energy we call the total mechanical energy. This is conserved quantities. Sum of the K and the U doesn't change with the positions. So we said total mechanical energy E is conserved. Then I'd like to show the conservation of mechanical energy from the equation of motions. So this is the equation of motions. Ma equal F. A equal dv dt and minus mg. Then you can multiply it. B equal dx dt. So you can multiply it. Here it's a v. This is dx dt. And you will get these equations. Same equation with the equation of motion. Then considering the term on the left hand side, so mb dv dt. This is equal to dt 1 over 2 mv squared. So from the left to the right, it's quite difficult, but it might be easy to show from the right to the left. So if you consider the d dt 1 over 2 mv squares, then 1 over 2m is a constant quantities. You can move outside of the derivatives. Then you can apply the chain rule. dB squared dB dB dt. Then this part is equal to 2v. So it becomes 2 is going to be cancelled out. So it's mv dB dt. So this is equal to the left hand side. So I show this relation. So left hand side can be converted with this derivative of the 1 over 2 mv squared with respect to times. And minus mg is a constant. You can easily move inside of the derivative. This one. So right hand side and left hand side is this becomes d dt 1 over 2 mv squared d dt minus mgx. Then you can move the term in the right hand side to the left hand side and combine to get this equation. Derivative of this quantity becomes 0. So this means inside of the parentheses has to be the constant quantities. We call the constant energy. Okay. So from this equation, this indicates that the equation of motion is equal to the energy conservations. Okay, when the work to stretch the springs, we'd like to find out the potential energy of a spring. Then we have to apply the external force to stretch a spring, F equal kx. Then the work done by the external force can be calculated. Is a 1 over 2 k x sub 2 square minus x sub 1 squares. So this is equal to the change of the potential energy. So we could find that the potential energy, we call the elastic potential energy by the spring, can be calculated. 1 over 2 kx squares. This is the potential energy stored in a spring. Okay, so if you draw the curve of the potential energy, U is a parabola, is a 1 over 2 kx squares. Okay, we could draw this type of the curves. Then again, we can start with the equation of motions to find out the potential energy of the springs. Ma equal F. F is a minus kx. And if we multiply V equal dx dt in the both sides of the equations, similar equation with the last ones. The left hand side is exactly same, and the right hand side is very similar to the left hand side. So instead of A, we choose a K. Instead of V, we move the X. Instead of V, it's going to be X. So we use a very similar equation to this ones. So easily we could express. This becomes a derivative of the minus 1 over 2 kx squares with respect to t. So left hand side is a d dt 1 over 2 mv squares, and the right hand side is d dt minus 1 over 2 kx squares. Move the right hand side to the left hand side, come to this equations. So derivative of the inside of the parentheses, this quantity becomes a 0. So this means that this quantity is constant. So sum of the kinetic energy and the potential energy, the elastic potential energy of a spring is a constant. This is a conservation, mechanical energy. So oscillations under the gravities. So in this case, the equation of motion, ma equals F. So equation of motion, this is ma equal F. So for the F, force from the spring and also gravitational force is acting on the object. Then multiply again v equal dx dt, the both sides. Then this equation b dx dt, dx dt here. Then this part is d dt 1 over 2 and v squares. This part d dt minus 1 over 2 kx squares plus d dt minus mgx. Then move the correct all the term to the left hand side. We have this equation. So inside of the parentheses have to be the constant quantities. So this is a total mechanical energy is conserved. But in this situation, first term is correspond to the kinetic energy. And the second and the third is a potential energy. Is a spring, elastic potential, and gravity. Last topic of this section is the gravitational potential energy. Magnitude of the gravitational force is depend on the position from the object. We consider the object of the M is changing the position from the R sub 1 to the R sub 2. The gravitational force is acting between the object Earth and this object. This is the minus g m sub e m over r squares. To find the potential energy, we have to apply the external force, exact same amount of the magnitude, and the opposite directions. So this negative sign becomes a positive. The total amount of work done by the external force. So this is force. To calculate the work, you have to integrate with respect to r. So this integral becomes minus gm sub e m over r. If you consider derivative of this quantity, it becomes 1 over r squares. R sub 1, r sub 2. So it becomes this equations. So we could define the gravitational potential energy is this equation. Minus gm sub e m over r, the gravitational potential energy. Once we find the gravitational potential energy, we could find the escape velocity. Escape velocity is the minimum speed that allows a rocket to escape from the gravitational field of the Earth. So conservation of the total mechanical energy said sum of the kinetic energy and the potential energy should be the constant. This quantity, this is the conservation of the mechanical energy. Though this is the Earth, the rocket is moving with the speed of the v, and moving. Finally, its r go to the infinities. In this position, velocity becomes 0. Velocity is decreasing when the rocket is moving away from the Earth. Speed is decreasing. When the rocket is reaching the r to the infinities, velocity is going to 0. So this is the minimum speed for a rocket to escape from the gravitational field of the Earth. So kinetic energy, V equals 0. So kinetic energy is 0. So R go to the infinities. Potential energy is 0. So total mechanical energy is 0. So from this equation, we could find the escape velocity. So this is the V sub escape equals square root 2g m sub e over r sub e. R sub e is the radius of the Earth. This is the radius of the Earth. So rocket is starting from the surface of the Earth. So we take a radius of the Earth. Okay, this is the end of this session.